Hi class. In the last video we talked about separation of variables in the case when both of the variables we were separating in were space. Now I want to do an example, the one-dimensional heat equation, where when we separate variables, one of the variables we're separating in is actually time. So let's consider a very long, thin bar or rod. We'll label it so that one end of the rod is at x equals 0, the other end of the rod is at x equals L, and is much thinner than it is long. So what we're going to think about is the distribution of temperature across this rod, where temperature can't flow out either side of the rod, but instead it can only flow out the ends. We're going to hold the ends of the rod at temperature 0. We're going to start, that's represented by these boundary conditions here. We're going to start with the temperature initially at time t equals 0 at some initial temperature t0. Let's say that temperature is positive. What's going to happen is heat's going to flow out of either end of the bar, cooling the bar. The equation that represents the spatial and temporal, that is the variation both in space and in time, the spatial and temporal temperature distribution is the heat equation. d capital T dt is equal to some constant kappa, the diffusion or heat constant, times del squared of T. Here, T is a function, capital T is a function of x and time, tells you the temperature at any given location x and any time t. And again, we're neglecting the variation across the length of the bar. We'll come back to that in the next video. It's important to understand the physics behind the heat equation. The temperature at a given point changes because heat is flowing into or out of that point. And heat flow is related to the variation of the temperature, the gradient of the temperature. In fact, kappa times the gradient of the temperature up to an overall minus sign is actually sort of a current associated with heat. And the divergence of that current talks about the net amount of heat flowing into or moving out of a point. And that's why the temperature rises or falls. So that's the physical meaning of this heat equation. Now, we'd like to solve this equation, the heat equation, subject to these boundary conditions, that the ends of the rod are held at fixed temperature, and that the initial condition, that the rod is initially at some temperature T0. In order to do that, we first look for simple solutions of the form where the function capital T is a function tau of time and a function x of space. Again, standard lecture number 35. It's not the statement that all solutions of the heat equation are of this form, but first we start by looking for solutions of this form. We plug in this equation into here, and on the left-hand side, when we take a time derivative, we just get tau dot times x. And on the right-hand side, here I've switched notation, unfortunately, in the constant I'm calling capital D, whereas here I called it kappa, is d times tau times the second derivative of x. We denote the time derivative of tau as tau dot. We denote the ordinary second derivative of capital X with respect to x by capital X double prime. If we divide by tau times x, we get an equation also rearranging the d, that's 1 over d tau dot over tau on the left-hand side is x double prime over x on the right-hand side. On the left-hand side, we have a function only of time. On the right-hand side, we have a function only of space. The only way that a function of time can equal a function of space is if they're both equal to a constant, the same constant. We'll call that constant minus k squared. As denoted here, for reasons that we'll see physically, we expect that k squared is going to be positive, a positive real number, so minus k squared will be negative. So, by using this trick of separation of variables, we've taken our partial differential equation and turned it into these two ordinary differential equations, each of which we know how to solve. The first one was very simple. 1 over d tau dot over tau is minus k squared. It's the first order equation. When we solve it, we see that tau of t is proportional to e to the minus d k squared times t. Now we can see why we thought of the separation constant negative k squared as being a negative real number. As time little t goes to infinity, that naturally goes to 0, which is what we expect to happen to our rod. We expect that the temperature in the rod is ultimately going to go to some constant. In this case, it's going to go to the constant 0. So that's the time that's the time equation. The space equation is just the harmonic oscillator equation. Capital X double dot over x is minus k squared. We get the solutions we got last time. capital X of x is some constant times cosine kx plus another constant times sine kx. It's worth checking dimensions. If you look back on the previous page, you should be able to show that the dimensions of the separation constant k are 1 over length. You can see that here as well, x double prime over x. The dimensions of capital X drop out. That just has dimensions of 1 over length squared. Therefore, k has dimensions of 1 over length. The diffusion constant, in order to make the equations in the heat equation work, has constants of length squared over time. So d times k squared has units of 1 over time. So e to the minus d k squared times time is e to the minus a dimensionless number, which makes sense. Also, kx is dimensionless, so that makes sense. We have to impose our boundary conditions now, that at position 0 and at position L, the temperature is held fixed at 0. When we plug that into here, x of 0 equals 0, it immediately tells us that we need a capital A equal to 0. If x of capital L is equal to 0, b sine kl is equal to 0. We have two possibilities, either b is equal to 0 or sine kl is equal to 0. b equal to 0 is a pretty boring solution. It just says the function 0 all the time, so that isn't the right choice. And therefore, we get this usual quantization that we find when we impose the boundary conditions, that k is n pi over L, where n is an integer, positive integer, 1, 2, 3, 4, etc., just like we did last time. The boundary condition quantizes the separation constant. That is a general feature that we are going to see over and over and over again. Therefore, any function of the form e to the minus d n squared pi squared t over L squared times sine n pi x over L solves the heat equation and the two boundary conditions. Note that the equation connects the spatial variation, n here, little n here, with the time variation. The same n appears here in the exponential. That's because we've set the separation constant k, which connects the time equation to the space equation, to n pi over L. Any function of this form satisfies the heat equation and the boundary conditions. We still haven't used the initial conditions, however, but we can use the linearity of the equation just as we did last time, and if a function of this form satisfies the equation, so does any linear combination. We have an infinite number of solutions, so in general our solution could be any linear combination of these solutions where we sum over any n, little n going from 1 to infinity, of this exponential behavior and this spatial behavior. Now we can plug in the initial condition. At time t equals 0, capital T is just a constant, t0, and it's the sum on n sine n pi x over L. This is just a Fourier series expansion, just like we had last time. We want the Fourier series representation of a function, a Fourier sine series representation of a function, which is 0 between capital 0 and capital L. And because it's a Fourier sine series, we extend it as an odd function. We make it minus t0 from minus L to 0, and then we extend it periodically with length L. That'll allow us to get a Fourier sine series representation of the constant. And just like last time, this is exactly the same as the kind of series we needed last time. A sub n is 4t0 over n pi for n odd, and it's 0 for n even. So again, the initial condition allows us to solve for these unknown coefficients, and in fact the unknown coefficients just give us a Fourier series expansion of the initial temperature distribution. So here's what the function looks like when I put it all together, and this actually is formally a solution of our equation and all the boundary and initial conditions. This, in principle, for any position x, any time t, we just sum this series up. We can do numerically approximate it, maybe by just taking the first few terms. That'll give us the value of the function capital T, the value of the temperature, at any position at any time. So a couple of notes before we conclude this segment. The functions sine n pi x over L each have a definite time dependence. Notice each sine n pi x over L, each spatial distribution of the form with fixed n, goes with a particular temporal distribution. This has a very special name. These kinds of modes are called normal modes, and the normal modes are just the spatial distributions that are associated with a fixed given temporal distribution. If we go out to large times, notice that these are decaying exponentials that we talked about before. At large times, we imagine that only the term with n equals 1 dominates, because if you plug in n equals 2, you have a 4 here, n equals 3 would give you a 9. So for large time, this is the kind of distribution of temperature you expect. The distribution of temperature is going to look like a sine curve, with 1/4 of a 1/2 of a period of a sine curve, and the overall envelope, the overall amplitude, exponentially decays. So this is exponential cooling. This is a general property we understand of cooling of any body. The bodies will cool exponentially. The characteristic time associated with cooling, if we just do dimensional analysis here, is 1 over d times the length squared of the bar. A larger bar will take longer to cool. Similarly, if it conducts heat more quickly, if d is larger, it will take a shorter amount of time to cool. So that concludes our discussion of equation. So let's summarize how we do separation of variables. And this is our general pattern we're going to see over and over and over again. First, you think about the equation that actually describes your system, and you figure out what coordinate system can be used most conveniently to express the boundary conditions. In our case, we've always been dealing with square plates or with rods, so we've been using rectangular coordinates, but in other situations, polar or spherical coordinates can be more useful. We write down the equations, the boundary conditions, and the initial conditions. We find special solutions, separated solutions, and we apply as many of the boundary and initial conditions as we can. In most cases, this implies just imposing the boundary conditions. Then we find the final solution by taking all an infinite series of all the special solutions that we found out here, and we apply any final boundary conditions or initial conditions to determine the unknown coefficients. This set of 4 steps are things that we're going to be using over and over and over again as we use separation of variables to solve partial differential equations.